Hello, everyone. In this week's QTFMS seminar, we will host Pavel Putrov from ICTP. He is going to talk about braiding on topological operators, anomaly of higher form symmetries, and the SymTFT. So, Pavel Putrov, thanks again for accepting our invitation, and you can take it away.
Yeah, thank you for the introduction, and I would like to thank the organizers for inviting me to present my work on this in this seminar series. So I was asked to give a talk about this paper done about this work done jointly with Rajath Radhakrishnan, who recently moved from ICTP to Oxford. So this is paper about studying kind of braiding structure on topological operators, which describe symmetries in the theory, and kind of the main idea here is study them from the point of view of the symmetry topological field theory. So let me start with some kind of general motivation. I guess many of you already kind of familiar with this modern perspective on these symmetries in quantum field theory, that we should view kind of more generally the symmetries as some kind of collection of extended topological operators. In particular, if we have a QFT in d+1 dimension, so we consider extended topological operators of dimension 1, 2 up to d, where d kind of corresponds to like codimension 1 operators. And in particular, when one talks kind of the very classical case of the usual ordinary symmetry described by some group, maybe we have some current J, so we can construct the usual Noether. Classically, it's a Noether charge by integrating the kind of Hodge dual of this current, which makes it in a D form over some D-dimensional subspace. So most kind of ordinary way to do this is to take this D-dimensional space and sort of a slice of my space-time with some fixed time. But in principle, we can do this for any codimension 1 submanifold. And so this, in particular, such integral exponentiated it's topological because of the current is conserved, and this kind of can be generalized, can be considered kind of, this is a motivation in a sense for the generalizations. So we consider kind of arbitrary arbitrary network of operators, maybe joining somewhere with some junctions, and so on. And mathematically, it's the kind of the structure which describes the behavior of these topological operators is believed to be a fusion D category. So I mean, this is a kind of a physics seminar, so I'm going to be quite lax about various. I'm not going to go into detail about kind of many mathematical subtleties which are present in kind of in this study of these fusion D categories.
Can I ask a question?
Yes.
For continuous symmetries, do we still have a fusion D category?
Well, most likely, literally, no, it cannot happen because, well, fusion in particular assumes that there is some finite number of simple objects. For continuous symmetry, you will fail at least at this,
So what's the corresponding structure?
Literally, it's not going to work, but one might. Well, I think there are some versions of this kind of generalization of these fusion categories where you relax this, try to relax this semi-simplicity in one, I mean, at least finiteness in one way or another. Yes, I think this appears in mathematical literature. But you have to deal, I mean, in some cases you will have to deal with, I mean, you have to define some sort of notion of, since you might no longer have sums, but you will need to consider some sort of analog of like direct, instead of direct sums, you can consider some analog of direct integrals. Yeah, and there is some sort of notions like this in the category. In my case, sorry, in the realm of this talk, everything will be finite, and all the categories will be semi-simple. Any other questions? well, yeah, well, I have not said much, but okay, let me review this, what happens in the kind of lowest dimension in 1 plus 1D. We can consider topological line operators. And so in this case, we consider just the ordinary one category, and the topological lines that correspond to objects in this category. And we can consider kind of junctions between lines, which would correspond to morphisms. We can pictorially understand in this way. So A is one object and B is the other object, and then we consider kind of junction between them, which correspond to some morphism from A and B. So the space of all, as usual, the space of all morphisms between A and B, between objects and B, is denoted by home. And then, well, we want additional structure which would physically correspond to fusion of lines, and mathematically this corresponds to some monoidal operation, which in a sense, to generalization, the most abstract way to understand the kind of generalization of a tensor product on the category. But again, the kind of physically, this means that we collide two topological lines together. And so in particular, we can consider kind of, in this setting, we consider junctions of operators. And if we kind of read this diagram from bottom to top, right, we started with pair of lines, and which we know the pair of lines as here correspond to a tensor product. And we end up with just one line. So in order to define such junction, we need to choose some element of a home from A tensor B to C. So some morphism from A tensor B, which we have at the bottom, to C, which we have at the top. So this is what we need to put kind of, in a sense, this can be understood. The space of homes comes to the space of local operator, kind of point operators you can put at this junction. And again, so usually there is this assumption of semi-simplicity that any object can be decomposed in the direct sum of so-called simple object, maybe with some integer multiplicities ni. Well, physically, the direct sum means like whenever we insert this kind of non-simple operator in my kind of path integral, then we consider kind of the corresponding superposition of insertions of simple lines. And these simple objects in particular, they satisfy this property that the only possible junction between pair of simple objects are, well, if the two simple objects are different, then there is they cannot be kind of joined. And if they can be joined, there is basically they can be joined in a unique way up to, of course, up to just some scalar multiplication, which tells us this space of homes between Ci and Cj is either zero-dimensional if I is not equal to j, or one-dimensional if I is equal to j. Okay, and well, yeah, there is some additional structure, a more subtle structure, which kind of is not seen just from this kind of fusion properties. It's what's sometimes called associator, or in physics literature is often referred as F symbols. And this can be understood as follows. So we can consider a pair of junctions, so which correspond, like we first fuse A and B, and then we fuse the result with C, or we can do it in the other way around. We first fuse B and C, and then we fuse it with A, then we get something. So in both in both cases, we have to choose what we put this kind of what we put on these two blue dots, which are local operators, kind of localized at this junction. And in both cases, these these choices give me describe all possible ways to go from A, B, C to D. But this kind of gives two different natural bases on the way we fuse kind of on the fusion space from A, B, C to D. This gives two bases, and this F symbol can correspond to can be understood as a way to go from one basis to another. Like more specifically, if I put some sort of particular basis element here and here, the result on the left-hand side will be given by a linear combination of the result of the right-hand side. Here I fix some simple object here, and here on the right I sum all possible simple objects here and choices of bases here and here. But kind of more abstractly, this can be showed as coming from the fact that this there is some sort of, we have to choose a kind of we choose some kind of non-trivial isomorphism between these two Hom spaces. One kind of which also can be stood as having a non-trivial isomorphism between these, making the tensor product in a different order. But in this way, again, using this kind of, by choosing the basis in the Hom spaces, everything can be very explicit. So this F is just collection of some numbers, F symbols. And they must satisfy these consistency conditions, which are kind of certain nonlinear equation on F, which come from the fact that we can kind of consider a sequence of this relation in this type of loop. And if you go in this way, apply to F changes in this way, and apply it three times here, we must get the same thing. And this is called the pentagon equation. And well, the choices of such kind of F can be understood as a kind of the data of F symbol can be in a sense understood as a 't Hooft anomaly of my symmetry. And why is that? Why it's kind of one possible way to interpret this kind of understand the 't Hooft anomaly in this kind of non-invertible case is because when everything is invertible, so we have line operators labeled by just elements of the group, and they fuse according to my group relation. Then this F, the choice of F symbols is equivalent to choice of the Srikos cycle on group G. So this Srikos cycle will determine, will specify this relation. And this is indeed known, this Srikos cycle is indeed, this third cohomology group indeed is known to classify 't Hooft anomalies of the global symmetry G in 1+1 dimension. And so this invertible case is often referred, like the corresponding category is what is called vec category, the category of vector spaces. Vec G means that the category is graded by G, and omega is this choice of non-trivial choice of associator, which one can introduce. Okay. So this is a very brief review of fusion categories. Is there a question, or there is some sort of hand raised?
Hi, good morning to everyone. I have a question. When you write the sum of F, you are telling that you are taking a sum in the Hom. Did it have a structure that we can add, or you are taking in some sense equivalation relations in the Hom? It's not clear for me. Why you?
Let me make it clear. So if I want to make it super explicit, it means I choose some particular elements here, A, B, and also choose some particular, I need to fix this extra data. So E is the choice of my line operator kind of in this intermediate channel, and alpha, beta are choices of these of kind of fusion channels, like when we, like alpha in particular.
You are writing?
Okay. Yes.
Yeah.
Can you see?
Yeah. Right now, see.
ABE and so on. And here I also make some choices. Gamma, delta, and F. And then, well, basically I need to sum over all gamma delta f. And this f symbol, it will depend on this, well, all these, well, everything which which you have here, it will depend on. Yeah, but of course, yeah, there many cases, there are a lot of cases where these, the home spaces, kind of the fusion coefficients are just ones and zeros. This means that these home spaces are one-dimensional. Then there is basically, there is no choice of label alpha and beta. I mean, I can more explicitly, I can choose this to be basis. Yeah, if I want to really make it explicit, I choose this to be basis elements. Well, something tensor, something.
Okay, so it has a structure in the home.
Yeah, so we kind of yeah. So if I want to put a like particular really actual network in my kind of space time of the theory, I have to like network of line operators. I need to specify, well, I need to tell what are all the lines, including this intermediate line E here. And I also need to specify what I put on these junctions. This is extra data I need to specify. And the statement that whatever, the expectation value of the network which locally looks like this is the same as the linear combination of expectation values of another network which locally looks like this. And this is the coefficients in this linear combination.
So, yeah, thanks.
Any other questions? However, like if you can see the lines we still consider line operators, topological line, but in 2+1 dimension, in 3 dimension. So now they can also kind of go around each other. They can braid. They can form some configuration like this. And again, mathematically, the braiding can be understood as kind of for each pair of A and B, I need to specify this kind of map from A tensor B to B tensor A in a different order because I kind of my tensor product this can be in principle can be sensitive in the order. Okay, and again, but geometrically it forms it just means that like if you understand these kind of these lines as onions, it means one onion goes winds around the other onion, kind of 180 degrees, and this there's some consistency. There's some consistency conditions that should be compatible with fusion structure, and in particular, without going into many details, it's I mean one of the compatibility conditions is essentially equivalent to this Young-Baxter equation, which means we can slide, we can kind of slide the fusion under or under some kind of one strands. Or in other ways, this kind of the braiding is a way to say the braiding is commutative with the fusion. And the other is this what is called hexagon equation. This is the most non-trivial one. And again, it can be understood as a kind of if I start with some kind of configurational lines, geometrically understood in this way. Start with some configurational lines and apply kind of sequence of these F moves and these braidings. I can kind of go around some loop and this gives me some self-consistent conditions as a kind of the product, which basically the product of 3 Fs together with the product of 3 Rs with maybe some of them may be inversed, it should be equal to identity. Again, if one wants to kind of actually write some explicit equation on some sort of bunch of complex numbers, so yeah, one needs to choose this basis in these junctions. Okay, And so yeah, mathematically, such kind of, if you have such additional structures, then the category is called braided fusion category. And this braiding can also be interpreted as a kind of part of 't Hooft anomaly, but now of kind of 't Hooft anomaly of the symmetry described by topological lines in 2+1 dimension. And again, this kind of interpretation is consistent with invertible case, where we consider invertible one-form symmetry in 2+1D. So where the lines are labeled by some elements of a group gamma, which must necessarily be abelian. And in this case, kind of analogously to anomalies of the kind of usual zero-form symmetries, it will be classified by the fourth cohomology of this kind of second classifying space of, sorry, this should be gamma, of course. Of gamma in U. And which indeed this cohomology class determines the braiding. In the case we have a kind of lines which are labeled by some group gamma, and again the fusion of these lines is just described by the group law in gamma.
So is this a one anomaly of the one-form symmetry? Like the H4 labels the one-form anomaly?
Well, the one form corresponds to the fact that it's this is a classifying space of one group. So in general, kind of yeah, for Q-form symmetry, it will be B Q+1 gamma, which is, I mean, also known, yeah, for in the case when it's a discrete group, it also has this integration of Eilenberg-MacLane space.
Okay.
And these four, it's well, in this case, it's 3+1, so it's always the cohomology group is always just dimension +1.
So this is not like a higher anomaly. It's just an ordinary anomaly of the one-form symmetry.
Yeah, yes, it's well, in general, if you have some sort of invertible, higher some sort of higher group symmetry, which means, I mean, which means basically in the category all morphisms, in the category all morphisms are invertible. Then yeah, the anomaly is just classified by, well, okay, there's some subtlety, like, okay, in 3D, yeah, it's just classified up to some subtleties, which I can mention in a moment. It's classified by just cohomology group in degree dimension +1. And the subtlety is that the actual classification is actually this should be Bordism classification. There should be not a cohomology group, but Bordism group, but I don't want to go into details. But in simple cases, these Bordism groups, they coincide with cohomology groups.
Okay.
Yeah, and this is kind of can be understood as a, yeah, this just classifies kind of invertible quantum, in this case, invertible topological quantum field theory with this symmetry in 4 dimensions. So in this case, the theory can be understood as living on the boundary of invertible topological quantum field theory. Anyways, yes. So it's natural to kind of ask the following question. So if you have if you know, for example, fusion structure of the of my topological lines, can we classify braiding? So can we kind of promote like line operators, kind of the symmetry given by some line operators to like from 1+1D to the symmetry of line operators in 2+1D? And well, one can approach this in a kind of very straightforward, kind of direct way. It's just we need to, like, if suppose we know this F symbol, so I need to find these solutions of hexagon equations. But there's some sort of nonlinear, complicated system of nonlinear equation. This in general, I mean, this has been done in some cases, but in general, it's a difficult way to do it. And so we want to consider a kind of alternative method using symmetry topological field theory. Okay, let me, again, many of you probably heard about this concept, but let me briefly review it. So we have
I'm sorry, I have a question. Can I ask?
yes.
In the previous slide, sentence. So finding the solutions of hexagon equations means getting the value of F and R, right?
Well, here we're asking the question, suppose we already know F,
Okay.
we already know a solution of a pentagon equation. But now we need to find R, which would be compatible with this F. Yes, we want to ask this type of question. Because it's, yeah, here I'm kind of, because like if you need to like classify braided fusion categories just from scratch, yes, then we would need to, I mean, this is even more difficult question. So we need to find also, like, we first need to classify fusion categories, which already very not trivial task. But here we're asking, suppose we know the category is fusion category, can we see what are possible braidings on it?
With the knowledge of F and R, we can classify all
yes, here, for our approach, it would be important that we know F, we already know F. But now we need to, I mean, first, I mean, there's also a question if it might not even exist for given F.
Okay, thanks.
So this, the symmetry topological field theory in this case can be understood as a three-dimensional, topological quantum field theory, such that my quantum field theory can be understood as kind of in this sandwich contraction. So I start with my symmetry TFT on some interval. And on one side, on this black side, I put topological boundary condition. And on the other green side, I put some other in general non-topological boundary condition. And the statement is kind of this, effectively, if I kind of collapse this interval, then this will describe my QFT. And in particular, kind of the, well, we know the kind of on this, in the QFT, the line operators are described by some category C. And the statement is that in this bulk SymTFT, the line operators are described by kind of fusion category, which is known as Drinfeld center of the C, is denoted by Z of C. And it is automatically braided fusion category. So it has, I mean, which is what we want because now it's in three dimension. And so, yeah, basically this is some kind of machinery. Input is a fusion category, and the output Z of C is a braided fusion category. And well, more kind of explicitly is constructed in the following way: the object in my new category Z of C are pairs, where the first entry of the pair is just an object in my original category C, and the second pair is a kind of essentially the choice of this of such kind of morphism between the tensor product of objects, where one of the objects is fixed to A, and here dot can be anything, any other objects. And this can be interpreted kind of the way for I prescribe how kind of each of these can give a different prescription. Each of these choices of AA gives us some sort of a consistent prescription how I can braid all possible B's around my given A. and it satisfies some compatibility conditions. And then one can consider what is often referred as forgetful functor from the center of C to C, which kind of, again, physically we can understand as we send, we start with some line operators in this bulk SymTFT, and each line operator gives me effectively some line operator on this QFT. These are operators which kind of survive once I squeeze this interval. And the operators which do not survive, so exactly, there are some operators which can, line operators which can end on this topological boundary, and they are not going to survive. So that's why it's kind of non-trivial map. And kind of roughly, you can understand it's kind of half of the operators will be killed. I mean, half meaning square root. Okay, and the main idea behind this kind of using this SymTFT to describe the braidings on my on these line operators, for which we only know fusion, is that in this way I can understand that the kind of the choice of braiding is equivalent to the choice of some inclusion of C to the center. So we always have a map in opposite direction. So kind of if you know some line operator in the center in the SymTFT, it kind of projects to some map to some line operator in this C, which happens after I squeeze kind of this interval to get effectively my quantum field theory. And this kind of, the inclusion should be such that if I apply this forgetful functor back, I get the same element. And kind of, well, first, kind of intuitively, it works in this way. So if I have some prescription how to, basically I, the inclusion gives me some sort of prescription to push, kind of pull the line operator which lives on this boundary to pull it into the bulk, and then in the bulk when we have it extra dimension, we can braid it around the other line operator. But more mathematically, this means the following. So if I have some object A and C, some line operator in my original category, I can suppose there is a way to include it into some into Z. So the image will be some line operator kind of object in the center of this form, and this the second entry. So if I know that the braiding on A exists, I can use this braiding exactly to construct this map, because well, as I said here, the second entry is exactly the kind of the prescription how I braid all other operators around A. So this is kind of this gives me some particular choice of this prescription, and then it will satisfy, since F just forgets the second entry, it will satisfy this condition that if I go around this way, if I do the composition, it gives me C back. Okay, and well, and the other way around. So if so here I can argue that if this C has some sort of braiding, then it gives me inclusion. But the other way around also works. This is because well, if I know that this C is included, so I know that this Z of C has braiding. So this kind of the restriction of this braiding on the image of C gives me some braiding. I mean, yeah, in a sense, yeah. Any questions? But again, kind of if you forget about like intuitively, the main kind of idea is that you will know the braiding because yeah, we know how the operators braid in the bulk, and if you know how kind of is there a self-consistent way to pull out operators from the boundary to the bulk, this will do the job. And well, the self-consistent here means that this inclusion is an inclusion as fusion category, so it respects the fusion rules. It is kind of the fusion structure. Okay, so using this kind of understanding, we can conclude that the classification of braidings on the C reduces to kind of considering images of essentially reduces to consider images of these kind of the fusion category C inside the center. And such images, well, which can be understood as some subcategories D, are such that their dimensions, of course, should be the same as C, a dimension, yeah, the dimension of C. And here by dimension, we understand this kind of quantum dimension, which is a sum of squares of quantum dimensions of simple objects. And for each simple object, the quantum dimension is basically expectation value of this line operator, a kind of small contractible loop. And well, another condition that is that this D doesn't contain lines that can end on topological boundary on this other. So it shouldn't contain as objects. The objects in D shouldn't be any lines which can end on the bound on this on the other side on the topological boundary. This is because since they can end on this boundary, they become trivial after I kind of collapse this interval. So we can just put, because we can kind of push them on this topological all these line operators. We can always push line operator on this non-topological boundary. It might give something or not, but if you know that since you can also push it here and it will disappear, then it must give nothing. It might also give nothing if I push it on the other side.
Can I ask something to clarify? So
yes,
is this like an obstruction to choosing Dirichlet boundary conditions for certain line operators?
well,
should I think of it as an anomaly or something else?
Abstraction. So what is abstraction? The choice? I mean, this condition? You mean?
Yeah, like since some of those lines cannot end on the boundary, means like we cannot choose the Dirichlet boundary conditions.
On the line, well, in a sense, yes, because I mean this can be. I mean this boundary condition can be understood as some boundary condition, as some sort of Dirichlet boundary condition on a certain subset of lines. Basically, and this yeah, this
But is D in any way related to a Toft anomaly? Or it's not?
well, it's related in this not a direct way. It's well, it will be directed in the way that it will be directed in the way that the Toft anomaly again can be a part of Toft anomaly. It can be suited as the choice of braiding, and in this approach, the choice of braiding is a choice of some subcategory D, which in a sense should be orthogonal kind of to all line operators which can end on this other boundary. But I mean directly this yeah, I mean Well, I mean, the kind of the choice of, well, one can also say, of course, things like the choice of this topological boundary condition is some choice of some Lagrangian algebra objects, and these Lagrangian object is basically some sort of contains a collection of can be so as a collection of line operators which can gauge self-consistently, and this, of course, it might be non-anomalous in a certain way. This can you can understand that. Kind of also that in this kind of you consider like you go beyond this boundary condition, and here you gauged this LC away. Kind of since you gauge them away, all kind of this kind of the orange line operators they basically disappear beyond the boundary.
I see. Okay. Thanks.
I also have a question.
Yes.
Is F the inverse of the pullback map? The iota?
Well, F itself is not invertible, but yeah, I mean, in a sense, the restriction of F on D, yes, is inverse. So roughly, yeah, the restriction. So we have a D going. Oh, let me write it here. We have F going here, and the point is F restricted on D is basically inverse of I. And D is some subcategory here.
Okay, I see. Thank you.
Yeah, F itself is not invertible because it forgets a lot of stuff, right? In particular, you can see here the F basically forgets all these the second element in this pair, this kind of this map. If you understand this, yeah, morally you should always kind of understand this. Well, not should, but you may always understand this. The center is roughly the number of objects is like square of the number of objects which you had before. I mean, to be precise, yeah, I mean, there's some way to make it more precise on the level of these quantum dimensions.
I'm sorry, I have a naive question. Can you once again explain how the images of I helps you classify braidings? Hello?
Yes, yes. Well, yeah, I guess I can show this the next slide. So, okay, the beginning of things. So yeah, the braiding. So if you have this inclusion, so yeah, basically we have a braid. So okay, D. Yeah, let me. So D is a subcategory in Z of C. So it has a braiding, right?
Yes.
Because it's subcategory of braided category, because we have braiding for, and then, well, we know that I mean C is F of D. So kind of, yeah. So F gives once I choose D, F gives me a kind of basically identification between objects in D and objects in C. Since we know braiding on D, this gives me braiding on C.
Okay, thank you.
And the other way around, if you have again, we can also argue if you know the braiding on C, then this braiding gives me this inclusion, which is this particular inclusion. Which is, I mean, this is a part of this follows from the definition of this, the definition of the center. What are the objects in the center? The particular for any if you can have a braiding on C, this gives me a particular this second element in this pair. And again, well, here this one can argue that these images must be some subcategories which satisfy these basically two conditions. This one, that the dimension of D should be the dimension of C, and the second one, which is D doesn't contain line operators that end on topological boundary, which mathematically can be understood in the following way: that the line operators that doesn't contain the line operators which end this topological boundary, they form these kind of Lagrangian algebra objects in this center, and which is, roughly I can do like a direct sum of lines which we can self-consistently gauge. It's kind of maximal combination of lines operators which we can self-consistently gauge, so that once we gauge them, we get a trivial topological theory. And and these but of course we need to know braiding on Z of C, but the braiding on the center is determined just can be determined from the F symbols. It must be, because we know that to construct Z of C, we only need to know C as a fusion category. So in practice, to do this, one can kind of to do this in a simple way. One can consider the following kind of algorithm in a sense. So we know F. Suppose we know F symbols on C. This is a kind of algorithm which circumvents this solving the hexagon equation. So we know F symbols on C, and so maybe this is too technical, but maybe for experts it will be interesting. But yeah, there roughly, but the bottom line is that there is some algorithm, but in order to kind of do this, first one considers what is called kind of tube algebra. And this is a kind of algebra which is formed by these kind of last saw type of junctions of line operators in C. And then there is a way from this tube algebra to recover S and T matrices of this center. So S matrix is basically tells me how these the pair of line braid. So this is given by S matrix. So for the kind of Hopf-Flink expectation value, and T matrix is basically, it tells me how if I have this kind of loop like this, how if I replace it by a straight line, I earn some phase, and this is the T matrix. And then there is this nice result by NG, recent result by NG roll when, which tells us actually once you know the F symbols, we can actually recover the full braiding structure just from S and T operators. So this is plus F symbols. And F symbols on the center, we know from the F symbols on this the C itself. Okay, this is just kind of the way to do this explicitly, but in principle, by construction, the braiding on the center should only depend on the it's only determined by this kind of fusion category structure on C.
Can I ask something?
Yes.
This algorithm is independent of whether boundary manifold is closed or open, right?
Sure. Yeah. This is just in terms of this local structure of the space-time. Yeah. Everything here depends only on the local structure of the space-time.
Okay, I see. Thank you.
All these kind of relations, we only need consider these relations as local relations. So they don't depend on the global structure of a space-time. I mean, again, we only need, our goal is only to kind of find this the braiding. I mean, how the braiding structure of the possible braiding structure between line operators, which is this kind of local operation. You can consider it's a neighborhood of a small ball. Yeah, and these all the topological, all these boundary conditions we share are local boundary conditions. They defined universally for any possible space-time topology. Okay, so it was kind of a description of general. So let me consider a very kind of super simple example, where this the category of is just what is called representation category of a group Z2. There's just two simple lines. Kind of the object in general for category of representation of subgroup is the simple lines, they correspond to a reducible representation of subgroup. Here is the group Z2, and they fuse just accordingly to how you consider tensor product of representation. Here, just two simple objects: the trivial one-dimensional representation and non-trivial one-dimensional representation. So here, basically, again, the group has one non-trivial element G, non-zero, and this non-trivial representation, the value of this non-trivial representation on G is -1. It acts as the G acts as multiplication by -1, and of course the fusion is just this. And of course, fusion of anything with 1 is the same thing. Okay, and the center here will be the category of lines in the untwisted dash graph Witten gauge theory for the gauge group G, which is Z2 here. So it would be, I mean, similarly, if I consider a general group G here, the result will be dash graph Witten gauge theory for this gauge group. And the simple lines there, again, for pairs are described by these pairs. Where one as in general, one element of the pair is the same as the choice of simple object in the original category, which is the choice of representation. And here the other object is the choice of the element of the group. So in general, these pairs which consists of the conjugacy class of some element of G, and rho is a rep of, okay, this is false in general. Let me, this is correct. The element of centralizer. Of G in G. Well, of course, if this group is abelian, the centralizer of any element is a full group. So you can also understand this kind of as electric and magnetic charges. The first entry is the electric charge, and the second entry is the magnetic charge. And here the Lagrange algebra for this topological boundary condition, which corresponds to kind of having symmetry C in this sandwich construction, is this. So it means that we can end on this kind of topological boundary, we can end these basically electric charges can be ended. Well, I don't know, it might be, okay, up to what you call electric and what you call magnetic. Yeah, the electric charges is what you can end on these topological boundaries. Is two lines, 2 out of 4 lines, which you can end, you have 4 lines in total, and 2 of them you can end on the boundary. And well, now according to this general position, you can consider subcategories such that, well, they have this dimension the same as the original category. Well, here all objects had dimension 1 because they're invertible. So it must have it must be 2 dimensional. So it need to contain 2 objects, and they shouldn't contain any lines which are already here. And this is only, I mean, it's easy to see that there are these 2 choices. of such subcategories. And one of them is gives a trivial braiding, and the other is gives me non-trivial braiding. In particular, in this case, this so here I have the second line is is a dion in my bulk theory, and it has a it has a kind of a spin 1/2, so it has non-trivial kind of cell braiding. So if I add this kind of loop, removing the loop gives me this -1 factor. Sure, yeah, and these kind of these are two images of this original category, which is contained, which was just generated by the simple objects 1 in P. So here, this P mapped to here, and here, this is one inclusion, and the other inclusion is that one goes here, goes to here. I mean, of course, here, I mean, it's super simple. This is like really overkill, but it's just to illustrate how to still kind of illustrates how this works. Any questions? Well, if not, I have the questions to you. I have to end in 5 minutes. Is this correct?
No, you can go on as long as you want.
Well, okay.
We do not have a restriction.
Okay, but still, anyway, yeah, similar analysis can be done for general in general case when the C is a category of representation of some group, and or C is this vec G category, which is I mean, this is just okay. This is a case when the line operators they fuse as a representation of some finite group, and this is the case when the line operators they just correspond to charges of some invertible symmetry G, and this omega is a Srikov cycle describing its anomaly in this kind of standard perspective. In all these cases, in both these classes, the center is just dash graph Witten gauge theory of gauge group G. Here it will be untwisted, and here it will be twisted with this Srikov cycle. And note that, of course, this rep G always admits, it is well known that it always admits at least the trivial braiding. And meaning like all operators, all lines braid trivially. But for this vec G, yeah, there is a non-trivial condition on the existence of braiding, and it admits a braiding if only if G is abelian, which is kind of natural because I mean essentially you want to promote zero form symmetry in 2 dimensions to 1 form symmetry in 3 dimensions in a sense. And of course, like for invertible case, we know that the 1 form symmetry it must necessarily be abelian. And there are also condition on this Srikov cycle is that if you consider these transgressions, what is called transgression of the Srikov cycle for some element G of my group, which is kind of considered as a function of pair of group elements, so H, K, and G, that this must be a Tuchel boundary. So in general, it can be a Tuchel cycle, but we require it to be a Tuchel boundary, so it's trivial in homology. And okay, and yeah, so another example one can consider from this perspective is this what is called Tambari-Yamagami category for abelian it's defined for a choice of abelian group A. Well, there are some additional choice of data, which which is not going to be important for me. But the fusion, in any case, the fusion is such that they are simple line operators corresponding to elements of this group A, and they fuse as for in invertible case, just according to my group law. But then I add some sort of what is often referred as duality defect, such that if I fuse this with lines corresponding to my group A, it just in a sense absorbs them. And if I fuse this M with M itself, the result gives me a sum of all lines corresponding to this abelian group. And using this SymTFT approach, which I described, we can easily reproduce the known result that the braiding exists if and only if this group is basically some product of copies of a cyclic group with two elements. And this this result, this is a known result which was obtained kind of in a more difficult way by just explicitly solving hexagon equations, essentially. So okay, so and now I want to consider generation to one dimension higher, and
Can I ask a question about the previous thing?
yes.
So is there a physical way to see why only Z2 to the power of M gives the braiding? Like maybe in terms of the Eisen model, or can we understand it from a physical reasoning, or is it just something that's mathematical fact that we cannot interpret?
Well, you can well, this SymTFT gives you some sort of, in a sense, I don't know, some geometric reasoning in some sense, but it's not. I don't have one sentence argument, physical argument for this, if that's what you want. Yeah.
Okay.
But I mean, essentially, there's some argument one can make that like in order, I mean, roughly speaking, this is because like when the braiding should be consistent with this Z2 comes from the fact that this kind of the product of these two guys doesn't contain any M. I don't know. We can give it in some sort of way. But I don't have a purely. In our paper we have some. We do some sort of give some sort of simple argument for this using this SymTFT, but it's not entirely physical. It's considering this some combination of these fusions, and this also you use also this tube algebra structure. You use some sort of combination, like some sort of the configuration of line operators like this. So it's not simple.
Okay, thanks.
I mean, it's still. I mean, the argument of braiding is simpler than classification, just solving a hexagon equation, but it's still not just one line argument. So now I want to consider generation to one higher dimension, and so in one plus dimension we can now have like in 3 dimension we can have not just lines but also topological surfaces. Mathematically, they're described by a fusion top category. So it's a more complicated structure. So again, I'm not going to go into all the mathematical subtleties of this definition of fusion top category. But the main idea is that, like, since it's a two category, you have objects, you have morphism, and you have a kind of morphisms between objects, and you have two morphisms, which are kind of morphism between one morphisms. And but you can like in the context of these extended topological operators, they all have a very nice geometric interpretation. In particular, well, the objects here, we understand as some sort of surfaces. Then we have morphisms, kind of arrows, which are kind of arrows between objects, can be understood as lines, kind of connecting two different surfaces, X and Y here. And of course, this gives you lines on kind of bound to these surfaces in general, but of course, it can be that the X and Y are kind of trivial surface, the kind of transparent surface, and A can be understood as just line operator by itself. And we have a kind of two morphisms, which are kind of mathematically can be understood as morphisms between kind of arrows of a different type between the usual arrows between one morphisms, and then they correspond to kind of junctions between these lines. And then we also want to add this fusion structure where we can, again, physically, this means that we can collide two surfaces together. And well, of course, the fusion on lines doesn't need anything separate, because the fusion on lines is actually is just a composition of this one morphism. So we can imagine here the second line, and the fusion is just actually a composition of one morphisms. Okay. Now we want to consider braiding. So in 3+1 dimension, the surfaces can braid non-trivially with other surfaces, and also can braid non-trivially with lines. But lines cannot braid with lines non-trivially in 4 dimensions. You can braid non-trivially only in 3 dimensions. We can always, like using this extra dimension, we can always kind of untangle any link we have. And again, there is a kind of a lot of things are quite similar, but also more kind of much more complicated in a way. But we still kind of mathematically we can describe this braiding structure on these surface and line operators using, in particular, kind of again the collection of this morphism between for any pair of objects X and Y. So kind of you can send this in this way. Of course, I mean I cannot. This is a kind of in a sense, three-dimensional projection of what happens in 4 dimensions. So here it looks like they pass through each other, but they actually don't pass through each other. They kind of, you should imagine that it goes here in this kind of 4th dimension and goes around it. But in any case, it gives me kind of, I can understand this in the similar way, in this kind of geometric way as a tensor product between, like at the bottom I have X tensor Y, and this kind of, if I understand order corresponding to this position of surfaces in this orthogonal direction, and at the top I have Y tensor X, and a fusion in which I can fuse in opposite order. And this, sorry, I want to define this kind of collection of one morphism, and this is again, this is one morphism because it can be understood as something which is like localized along one dimension, right? Here, the one morphisms were kind of in general configuration localized along one dimension, and in the two morphism are something which is localized like along the 0 dimension.
Can I add something about this?
Yes.
In 3+1 dimensions, can we also consider the braiding between line operators and volume operators? Does that give anything interesting?
Well, the volume operators are just kind of I mean, the volume operators are just kind of separate, essentially locally, they separate space-time in two pieces. So there is no kind of, not really, because they can only intersect in general. Yeah, there is no interest in braiding.
But like the line essentially goes through like different universes in the language of volume operators in 3+1.
Yeah,
so,
this is not, yeah, you can consider kind of intersection, yes, this is you can consider. But yeah, so this would be like this gives you some action of volume operators on the lines, yes. But this is not usually referred to as a braiding.
okay.
And here I don't want to consider this volume area because I want to start with something which is like defined, can live in 2+1D, and see if I can promote it to something which lives in 3+1D.
I see.
In a way.
I see. Okay.
So I don't, of course, I can consider also everything with this higher dimensional operator, but this is, I don't want to do. And but here the situation is more complicated in the one category here. So apart from this one morphism, one also need to consider some sort of a collection of two morphisms. I'm not going to write all of them. So in particular, there should be this two morphism which correspond to kind of between two, which is a two morphism between a pair of one morphisms, which are obtained by this kind of composing. So here I consider braiding between surface operator, and then I consider some line operator which changes x to x prime. But I can do this in the other way around. I consider this line operator which changes x to x prime, and then braid these two together, now x prime and y. And this kind of correspond to this kind of picture. So here I have this braiding one morphism, which is localized along this kind of line, and I have this the line operator A, which it changes x to x prime, and this is along this. Here I have this. This is where kind of this neighborhood is what describes me this two morphism, which is between this one morphism and this one morphism. But of course, in order to understand this way, I have to kind of read this diagram in this direction. So I kind of compose. I compose. This I have this pair of one morphisms, and then I have this pair of. Sorry, no, the other way. This is this kind of I consider kind of composition. This gives me a composition of some composition of one morphism. So this gives me some other composition of some other two morphisms. And this is a two morphism between these two compositions. Anyway, there are some two high category shenanigans which we can consider. And again, I'm not going to go into all these details. And they satisfy some a lot of compatibility conditions, which there's some rather long list. But they all have kind of some geometric interpretations. And basically the idea, we want to use the same idea to classify possible braidings on a fusion category. And again, there is a similar notion of the Drinfeld center. Now it's the Drinfeld center for fusion 2 category C. So the output of this construction is some braided fusion 2 category. And so again, formally it's defined in a similar way. So the objects in this new category is pairs. So where X is the object in the original category C, and now this EX is a choice of this. Sorry, of course it should be in the opposite order. And of course, plus all these two morphisms, which I have not listed all of them. Some similar two morphisms, and they satisfy some compatibility conditions. But again, physically, this center can be understood as what describes this topological quantum field theory now in 3+1 dimension, such that the sandwich construction, because it's now boundaries are 2+1 dimensional, gives me the 2+1 dimensional quantum field theory with this symmetry described by the fusion 2 category C. So again, here we have some sort of lines. We had some sort of lines and surfaces, and here we also consider some lines and surfaces. But here we know that in this 4+1D they can braid these lines and surfaces. And without going again into much details, similarly, the braidings on C, which is a category can be described by embeddings of C into the center, which is a larger category. And okay, so well, there's some argument which maybe I don't want to go into details, but yeah. So one can argue that actually, in a sense, in this in this case, plus one dimension, the situation in a sense is a bit more simple, actually. So because one can argue that, like, if C, suppose C does admit some braiding, some choice of braiding, then we know that the lines braid trivially, right? According to this braiding. And this, one can argue that if the category of some line operators has trivial braiding, it necessarily forms a representation category for some group H. But then one can consider gauging away all these lines, and we can, since they braid trivially within themselves, we can consistently gauge them away, since they have kind of no anomaly. And the resulting category, which we denote here by C prime, is not going to have any lines at all. And there was some argument in the paper by Johnson and you say that, like, if you have this only surfaces in a fusion 2 category, then this fusion 2 category must be basically describe some invertible symmetry for some group G and some choice of focal cycle. No. So this is a category where surfaces are just labeled by elements of the group G, and they fuse according to the group law G. And well, there are some anomaly, which is just usual 't Hooft anomaly, which is described by this choice of focal cycle. But then it means we can actually recover kind of, for any kind of gauging of topological operators, there always exists a kind of inverse operation where we gauge something else and we get the original category back. And in this case, well, since once we gauged the subcategory, which is rep of H for some group H, to recover C back, we need to gauge some symmetry H inside this. Basically, H is some group in this G, and therefore we conclude that the C admits braiding only if and only if it's what is called group theoretical. And group theoretical, well, by one of the definitions, is that it's obtained from the invertible symmetry described by some group G by gauging some non-anomalous subgroup H. And non-anomalous, in terms of this focal cycle, non-anomalous means that if you consider restriction of this focal cycle on H, it's must become trivial. In particular, this always means that the center of the C is just Dutch graph-Witten theory for this gauge group G. Okay. And we can use want to go through because actually quite a lot of calculations involved in this, but we can use which I'm going to present all this technical data. You just summarize the result. So we can use this SymTFT approach to obtain, in particular, the following results. First, that this 2 category where you just have a invertible symmetry G, it admits braiding only if this symmetry is abelian, and this focal cycle is trivial. So this is a bit, it's kind of similar to what we had in lower dimension, where we just had some vec G for some Srika cycle. There, the result is that, again, G must be abelian, but this there was a kind of weaker condition on this P, that all transgressions of P should be trivial. But here one can actually, there's some cohomology argument which we do in the paper that, okay, you also get the similar condition that all transgression of P, which is now focal cycle, should be trivial. But we can argue in this case, it actually implies that the cycle itself must be trivial. And well, we also consider this what is called kind of generation of Kambari-Yamagami categories, which I considered previously. There's some generalization considered by DKP and U to two categories. So there's some two category which is defined by the input. It's again some abelian group, and pi is some choice of the Fokker cycle. And the fusion rules are basically similar to what we had here, but now it's a fusion of surfaces, not line operators. And the result we obtain is that it's admissive braiding if and only if this A is again some number of copies of Z2, and pi is trivial in H4. Okay, yeah, that's all I wanted to say. Thank you.
Okay, thank you for the great talk. And we can have questions. And okay.
I have one question about so why would we be interested in braidings in this SymTFT context? Like, what would be the physical applications of these things? Because I kind of missed that.
So well, one part, I mean, why do we care about braiding again? So braidings, this is a braidings kind of part of anomaly. So in practice, for example, you sometimes you want to kind of classify. Yeah, so you want to consider if you want to classify. So if you want. And classify kind of gaugings, possible gaugings. We need to know so it's gauging of the global symmetry. We need to know braiding, the braiding structure. On the category. So kind of for you are, I mean, you have some sort of symmetry, and in your quantum field theory, and you are interested, like if you can gauge some part of the symmetry. Again, mathematically, these symmetries are described by some sort of certain algebra objects in this category, and yeah, and kind of well, it's good to know the gaugings, like if you can kind of figure out or you can kind of relate one theory to another theory, for example, by some gauging of some part of global symmetry. And again, but more kind of physically, you can understand that like if you have if you have kind of two line operators which have some sort of non-trivial braiding between themselves, you cannot simultaneously kind of gauge them away, gauge them. You cannot simultaneously condense them. Well, gauging in a sense can be stood as kind of you, or sometimes or like referred as a condensation in like condensed matter terminology. Like you can kind of you fill your space-time with kind of all possible networks of these of some sort of line operators. I mean, of course, and you choose some particular subset. You want to kind of say if you can choose some particular subset of line operators, which such that you kind of fill your space-time with these all possible networks of these line operators, and the kind of you want the result to be independent of this choice, which and this is the kind of gauge invariance. But of course, if this choice and this choice like different, then you already have an issue.
I see. And so if I remember correctly, in 2D, if we want to classify the possible gauges, for example, for non-invertible symmetry, it would be some sort of a Frobenius algebra.
Yes.
Can we say the same for higher dimensions? Like, what's the corresponding structure in that case?
Well, there is some mathematical structure. Yes, some sort of higher haploid symmetric Frobenius algebra. But in particular, it should be symmetric in a sense, like in 2+1D. Like, okay, this thing should be equivalent to this. Where in the dot I put the algebra multiplication.
You see. So the braiding structure kind of tells us about the kind of algebraic structure that we can use to gauge.
Yes. It gives a like if I need to find these algebras, I need they should have like in high dimensions, starting from like 3. They care about the braiding structure on your category. So
I see. Okay. Now I see more. Thank you. Thanks for the nice talk.
Do we have any more questions?
I have one question.
Mhm.
All these can be thinking in a quantum field theory, not topological. I mean, when you define all this theory, you are using strongly category theory, but the physicians, the definition should be as the variation of the observers with respect to the metric equals 0. It to me don't seem relevant that the variation with respect to the metric be 0 in all this theory. You are only using the mathematician focus using category theory and not really the connection between the observables of the theory, of the physics theory.
Well, I consider the theory itself, is not necessarily topological. In particular, this the theory which the theory itself is not topological. It's only this SymTFT theory is topological, but this the theory in the original theory where I consider this kind of these kind of line operators, topological line operators, all this stuff, they live in kind of they are topological operators in a non-topological theory. Well, generically, it's non-topological theory. So you can also, you also can have some non-topological operators in particular, which you cannot just move around freely. But you just focus on this class of operators in non-topological theory, which you can freely move around. So the theory itself is not topological. You just consider a collection of topological operators.
Mm-hmm. Yeah. Sorry.
Okay, in this picture, in this picture, which I considered in this Scottish picture, the theory, the theory in the bulk was topological, the SymTFT, yes. But this part in this, because this part is a non-topological boundary condition in general, and only this is topological boundary condition. So the result gives you effectively some well, if this was d+1 dimensional and this was in the bulk was d+2 dimensional, so the result effectively gives you some d+1 dimensional non-topological theory with symmetry described by this category C. And this the center of C was indeed a symmetry in topological theory, but this category it describes topological operators in non-topological theory.
Okay. Yeah, because to me, I don't know, don't see how it's related to the observables of the theory. This is creating a very
Well,
important.
yeah, I mean, okay, of course, to have this, you have to need to also understand how these topological operators act on non-topological operators. So this is yeah, so you need to consider this type of configuration where you have some sort of topological operators, and this is non-topological. And the way kind of, yeah, they surround them in some way, but the way kind of the way that topological operators can act in principle, yeah, on non-topological operators is restricted by your structure of just like structure of topological operator. How can they fuse with each other? How can they braid? This kind of this. But of course, yeah, in principle, yeah. I mean, the final goal is to also use this, and this can give you some sort of this. Well, the constraints on constraints on physical observables. Some sort of selection rules or whatever. So basically, yeah. You also, in order to start to actually study dynamics, to have some sort of implication on dynamics of these. If you want to get from this some restriction on the correlators on this kind of physical observables, you need to also study this, yes, structure, how this what happens if you move if you move around this topological operator in the presence of also like non-topological operator, some kind of wheel, like you can have some sort of engaged series and Wilson lines which are not topological, or some local operators which are not topological. You need to also describe this, what happens, but what can happen there again is already restricted by just, I mean, there will be also some self-consistency conditions, and there will be some sort of in a representation, the series of representations of this fusion category. Like in the usual case, we have an ordinary symmetry, which is some group, and this, well, the fields, they form some representation of this group. Similarly, we needs to consider generalization for this. When instead of group, you consider categories. But again, as in the group case, the representation theory, like what possible representation you can have is actually determined by the group itself. The structure of the group itself gives you a lot of condition. Similarly, what will happen in this in the case of the generalized symmetries, which might be non-invertible.
Okay. Thanks a lot.
So let's thank our speaker again. I think we can have questions off record now. We can stop the recording.